At 5:44 in the morning, the first flat of shell eggs reaches the breaking machine at a Michael Foods processing plant in the Midwest. The flat holds 30 eggs. The machine processes it in under 1 second. 30 shells crack simultaneously against precisely positioned breaking blades, the contents dropping through separation cups below that divide whites from yolks with mechanical consistency no human hand could match at this speed. Here the empty shell fragments travel one direction toward the shell disposal system. The liquid contents move toward the filtration and pasteurization line. The breaking machine handles more than 200,000 eggs per hour. At that rate, 200,000 eggs per hour. The machine processes a full flat of 30 eggs every 0.54 seconds. It does not slow. It does not fatigue. It does not misplace a yolk or contaminate a white with shell fragments at a rate the food safety system cannot manage. The measurement that defines Michael Foods' breaking capacity is not the number of eggs per day or the shifts per week. It is eggs per hour, because the breaking machine thinks in fractions of seconds. Michael Foods operates one of the largest egg products processing networks in North America. The company manages laying hen facilities with approximately 15 million birds and produces over 120 million pounds of liquid, frozen, and dried egg products annually. The Foodservice kitchen that cracks 3 eggs into a bowl for an omelet, the food manufacturer blending whole liquid egg into a cake mix formulation, and the institutional cafeteria that scrambles 50-pound bags of pasteurized liquid egg for a breakfast service. All of them trace their egg supply through a processing system built on the breaking machine running at 5:44 in the morning. Understanding how 120 million pounds of egg product emerges from 15 million hens requires understanding the specific problem that industrial egg processing solves, and why the shell egg itself, the most familiar form of the egg, is in many respects the least efficient form for the customers who need eggs most. The shell egg is an evolved biological structure of formidable protective engineering. The calcium carbonate shell contains approximately 17,000 microscopic pores through which gas exchange occurs for the developing embryo. The shell membrane, cuticle, albumin, and yolk each perform specific functions in the biological context for which they evolved. For a commercial kitchen buying eggs in volume, the shell is a problem. A restaurant that serves 400 omelets per day cracks 800 to 1,200 eggs per service, depending on egg size and the specific menu portion, using kitchen staff whose time at the cracking station cannot scale indefinitely with volume. Each hand-cracked egg carries a contamination risk. Salmonella on the shell exterior can reach the albumin through the cracking process if technique or sanitation lapses. Shell fragments fall into the product. The eggs arrive in 30 egg flats, which require refrigerated storage, inventory rotation, daily receiving, and the physical handling of fragile product through the kitchen's supply chain. And the separate cracking step adds labor that a high-volume operation accounts for in its food cost calculation. Liquid pasteurized egg eliminates every one of these problems simultaneously. It arrives in 30-pound bag-in-box containers or 5-pound cartons, refrigerated and ready to pour. The salmonella risk has been eliminated by the pasteurization step. No shells, no fragments, no cracking labor, consistent volume per container, without the natural size variation of shell eggs. A kitchen manager ordering liquid egg can predict product cost and kitchen labor with a precision that a shell egg order cannot provide. Michael Foods recognized this gap early and built its processing network to serve it. The breaking plants that convert shell eggs into liquid egg products are the industrial infrastructure that makes liquid egg possible at the scale food service and food manufacturing customers require. A food service distributor supplying liquid egg to 200 restaurant accounts in a region needs a supplier that can provide consistent volume, consistent food safety certification, and consistent product specifications week after week. At a Michael Foods network of breaking plants and the 15 million hen layer inventory behind them, supplies that consistency at the scale the food service supply chain demands. The 15 million laying hens that supply Michael Foods' breaking plants represent a production base concentrated in the corn and soybean meal producing regions of the Midwest, Iowa, Minnesota, Nebraska, and neighboring states where the feed cost advantage and flat agricultural land support large-scale layer operations. The commercial white leghorn hens in Michael Foods' facilities produce at rates optimized for breaking operation economics rather than shell egg retail economics. In the retail shell egg market, egg size grades, jumbo, extra large, large, medium, determine retail price, and a layer flock manager optimizes for the large and extra large grades that carry the highest retail premium. In the breaking plant model, our egg size matters primarily through its effect on the number of eggs required to produce a pound of liquid egg product. A smaller egg yields less total liquid per unit of breaking equipment throughput. The breaking plant wants consistent-sized eggs that run through the breaking machine without jamming the cup separators and that yield maximum liquid per egg at minimum shell percentage. The relationship between egg size and liquid yield is direct. A large egg averages about 2 ounces, here with the shell accounting for roughly 11% of the total weight, leaving approximately 1.78 ounces of edible liquid per egg. At 200,000 eggs per hour, the breaking line processes approximately 22,250 pounds of liquid egg per hour, 11.1 tons, before accounting for the 8 to 12% moisture that separation and processing may adjust. Michael Foods sources eggs from its own company-owned laying facilities and from contract producers who supply breaking-grade eggs under volume agreements. Are eggs that don't meet retail shell quality standards, slightly rough shells, checks that don't penetrate the membrane, slightly oversized or undersized, are perfectly suitable for breaking. The breaking plant's quality control focuses on the liquid content's microbiology and composition, not the shell's surface appearance. The supply logistics that move eggs from laying facilities to breaking plants follow a cold chain requiring consistent refrigeration because the vulnerability of the liquid egg to bacterial growth begins the moment the shell is compromised and accelerates with temperature. Shell eggs arrive at the breaking plant within days of lay, having been held at 45 degrees Fahrenheit or below through transport. The receiving dock's first check is temperature. A load that arrived warm triggers a detailed investigation and potential rejection. Inside the breaking plant, the sequence that converts shell eggs into pasteurized liquid egg products runs through 5 primary stages: washing, breaking, separation, filtration, and pasteurization. The washing stage precedes breaking and addresses the salmonella contamination risk directly at its source. The shell eggs passing through the washer encounter warm water at temperatures 20 degrees above the egg's surface temperature, a specification that prevents thermal gradient-driven absorption of surface bacteria through the shell pores. Combined with detergent and sanitizer at concentrations the USDA and FDA regulatory standards specify. A properly washed egg enters the breaking stage with a sanitized exterior, that the breaking machine's blade contact with the shell surface cannot transfer pathogens from. The breaking stage, at 200,000 eggs per hour, operates through a sequence of vacuum cups, breaking blades, and separation bowls that no layperson would recognize as an egg-cracking device. The machine positions each egg precisely against a breaking blade that strikes the equator of the shell with calibrated force, enough to fracture the shell cleanly without crushing or driving fragments into the contents. The fractured shell halves open over separation cups, 2 cups per egg station, one receiving primarily white and one receiving primarily yolk. Separation is not absolute. Some yolk enters the white cup, some white enters the yolk cup. The precision of the separation determines the product purity, the percentage of yolk protein in the white fraction, and the percentage of white protein in the yolk fraction. Breaking machine separation efficiency varies by equipment design, egg age, and the temperature of the eggs at breaking. Cold eggs break and separate more cleanly than warm eggs because the yolk membrane is firmer at lower temperatures and less likely to rupture during the separation motion. The filtration stage following breaking removes shell fragments, chalazae, and other physical contaminants that pass through the breaking machine despite the separation design. Multiple filtration stages, coarse straining first, then progressively finer filters, produce a liquid egg stream with the physical purity that pasteurization equipment requires. A fine shell fragment that reaches the pasteurizer heat exchanger creates an equipment cleaning event that interrupts production. The filtration sequence is not a quality option. It is a production protection measure. Pasteurization is the critical food safety step that transforms raw liquid egg, which in its natural state carries salmonella contamination risk at frequencies that USDA egg products Inspection Act standards cannot accept for commercial distribution, into a pathogen-reduced product meeting the safety standards that food service and food manufacturing customers require. The technical challenge of pasteurizing liquid egg differs from pasteurizing milk in a specific and important way. Egg protein is heat-sensitive at temperatures close to the pasteurization temperature required to eliminate salmonella. Milk pasteurization at 161 degrees Fahrenheit for 15 seconds poses no risk of protein denaturation because milk proteins tolerate that temperature range easily. Egg white protein, primarily ovomucin and ovalbumin, begins to denature at temperatures approaching 140 degrees Fahrenheit under sustained heating, and protein denaturation produces the coagulated, grainy texture that renders the liquid egg commercially useless. The pasteurization parameters approved for liquid whole egg, liquid whites, and liquid yolks differ for this reason. Liquid whole egg pasteurizes at 140 degrees Fahrenheit for 3.5 minutes, a lower temperature than milk pasteurization, one held for a longer time, that achieves the 5-log reduction in salmonella that regulatory standards require without the thermal damage that higher temperature, shorter time profiles would produce. Liquid whites require even more careful thermal management because albumin protein is more heat-sensitive than whole egg. Approved pasteurization parameters for whites run at 134 degrees Fahrenheit with extended hold times and sometimes additional alpha-amylase enzyme treatment. The plate heat exchangers and tubular heat exchangers that Michael Foods' breaking plants use for pasteurization control inlet temperature, hold time, and exit temperature with precision that the regulatory specifications require. because a pasteurization run that doesn't achieve the required temperature-time combination at every point in the product stream must be diverted and reprocessed rather than released to distribution. Continuous temperature monitoring via automated diversion valves for under-temperature product and JCCP critical control point documentation at the pasteurizer create the food safety verification record that SQF certification and customer audit requirements demand. The product forms that emerge from Michael Foods' pasteurization systems: whole liquid egg, liquid whites, liquid yolks, and specialized blends serve markets with distinctly different specifications and supply chain requirements. The liquid whole egg, pasteurized liquid containing both white and yolk in the natural approximately 60-40 ratio, is the highest volume product form and the primary input for food service scrambled egg preparation, institutional breakfast programs, and baking applications where whole egg function is required. It reaches customers refrigerated in bag-in-box containers ranging from 4 to 50 pounds, with a refrigerated shelf life of 8 to 10 weeks from pasteurization date. The shelf life depends on maintaining cold chain integrity through distribution. Every degree of temperature elevation above 40 degrees Fahrenheit accelerates the microbial growth that reduces shelf life. Liquid egg whites have expanded significantly as a product form driven by the consumer demand for high-protein, low-fat foods and the protein supplement market's need for high-quality albumin. A 30-pound container of liquid egg whites contains approximately 100 grams of protein per pound, a concentration that the protein supplement manufacturers using egg white protein in ready-to-drink products and the food service customers making egg white omelets depend on from a consistent, pasteurized, listeria-free supply. The frozen egg products extend the effective shelf life from 10 weeks for refrigerated liquid to 12 to 24 months for frozen, a supply chain option that food manufacturers requiring bulk egg ingredients in their formulations use to manage inventory without the freshness constraints that refrigerated liquid requires. Michael Foods' frozen products include frozen whole egg, frozen whites, frozen yolks, and a range of custom blends. Sugared yolk with added sucrose to prevent gelling on freeze, unsalted yolk for specific bakery applications that the food manufacturing sector specifies for industrial baking and confectionery production. Dried egg products push the shelf life further. Spray-dried whole egg powder, albumin powder, and yolk powder stored at ambient temperature for 12 to 36 months, depending on moisture content and packaging. See the spray drying process that converts concentrated liquid egg into powder, operates at temperatures and atomization parameters calculated to remove moisture while preserving the functional properties. Emulsification, foaming, coagulation, that the dried eggs food manufacturing customers pay for. A dried egg powder that has lost its foaming capacity during spray drying is not interchangeable with one that has retained it, even if the protein content is identical. The food safety infrastructure that Michael Foods operates across its breaking plants, HACCP programs, SQF certification, temperature monitoring, testing protocols, and USDA egg products inspection, reflects the regulatory and customer audit environment that egg products processing operates within. The Egg Products Inspection Act requires USDA continuous inspection of all breaking plants, meaning a USDA inspector is present and monitoring during all production hours, yet not conducting periodic visits. This is a more intensive regulatory presence than the USDA and FDA periodic inspection programs that apply to most food manufacturing facilities. The continuous inspection requirement reflects the food safety risk profile of liquid egg. A product that carries salmonella risk in its raw form requires controlled pasteurization to make safe and reaches food service customers at high volume in a form where any pasteurization failure could produce widespread illness. Michael Foods' BAID HACCP programs identify the pasteurization step as the primary critical control point. The step where the hazard of salmonella contamination is controlled and where deviation from the critical limits of temperature and time requires immediate corrective action and potentially product diversion. The temperature monitoring equipment at the pasteurizer generates a continuous record that the facility retains and makes available to USDA inspectors and customer auditors as documentation that every pound of product leaving the plant passed through the critical control point within its specified parameters. SQF, Safe Quality Food. Certification, maintained through third-party audits against the Safe Quality Food Institute's Food Safety and Quality Code, that provides an additional food safety management standard that food service distributors and food manufacturers increasingly require from their ingredient suppliers. Michael Foods' SQF certification is not a regulatory requirement. It is a customer requirement, reflecting the private sector food safety standard that the food industry has built above the regulatory floor. 120 million pounds of egg products per year, at 200,000 eggs per hour per breaking line, and a typical shell egg weighing approximately 2 ounces of liquid content. 120 million pounds of liquid equivalent requires processing approximately 960 million eggs annually, roughly 2.63 million eggs per day across the full network of breaking plants, at 15 million hens producing approximately 290 eggs per year each. Michael Foods' 15 million hen layer inventory generates approximately 4.35 billion eggs annually, a production volume that the breaking plants process, along with eggs from additional contract supply arrangements. The arithmetic of scale has a way of making a familiar product unfamiliar. The egg that appears in every household refrigerator, cracked one at a time into the pan, becomes something different when 200,000 of them flow through a breaking machine every hour. The shell that a home cook disposes of in a few seconds becomes the technical challenge of a separation system designed to remove it from a liquid stream at 200,000 units per hour without leaving fragments. The yolk that a cook can see and separate with a half shell becomes a product fraction that a mechanical separator divides from the white with 98% purity across hundreds of millions of eggs per year. The restaurant that buys Michael Foods' liquid whole egg in 30-pound bag-in-box units. The bakery that uses frozen whole egg in 30-pound cans for its production batches, and the food manufacturer that adds dried egg white to a protein bar formulation are all consuming the output of 15 million hens filtered through the breaking machines and pasteurizers and spray dryers of a processing network that converts the most basic of agricultural products into a precision industrial ingredient. The machine was running at 5:44 this morning. It is running now. It will run until the shift ends, and then the next shift will pick up where this one stopped. 120 million pounds doesn't pause. If this look at the breaking plant technology, pasteurization science, product form diversity, and food safety systems behind one of North America's largest egg products processing networks gave you a clearer picture of where liquid eggs actually come from and what happens between the hen and the food service kitchen. To hit the like button and help the algorithm find more viewers who want this level of detail. Subscribe for more deep dives into the processing systems that convert farm production into the industrial food ingredients behind everyday meals. Drop a comment and tell us where you're watching from. The range of locations in these comments always surprises us, and reading them matters every time.